Hello, and welcome to the Exploit Development 107 lecture. My name is Dr. Owen Redwood. This lecture is part of the Offensive Computer Security 2.0 OpenCourseWare, hosted by HackAllTheThings.com. For today's lecture, which is a new lecture, we're going to cover the following topics. Advanced exploitation topics, including format string exploitation and heap spray exploitation. We're going to talk about Clang, how it's recently been adopted by, or being adopted by all the major Linux distributions to compile the OS and applications and all the binaries that come with it. How the Clang stack and the GCC stack actually differ. How this affects exploitation. And finally, we'll have discussion on exploiting the Clang safe stack. Finally, we're going to wrap up our exploit development discussion in this course by discussing exploit mitigation suites. So we'll cover EMET, GRStack, PAX, kern heap, and so on. One topic I did not cover earlier during our format string exploitation lecture is the fact that for the standard notation, you can actually specify which variable on the stack to reference. And that is done by the number $sign modifier. So you have the %, the *c conversion specifier in a format string, and the S at the end specifies to treat it as a string, so a string pointer. And this says treat the sixth parameter from my current pointer as a string pointer. Dereference it and print it out to the screen or to the log or wherever its destination buffer is. So to explain how to use this in a targeted fashion, you can use a simple string that's just some number of letters and characters, and then a sled of %p's. And once you get the %p, or you could use x to just print out the hex values. Once you find your target, then calculating this precise addressing is simply counting the number of %p's or %x's that are converted before your target. So all it is the number of things up to that target, and that is n in this style of exploitation. It's pretty simple, actually. Now for heap sprays, we've talked about common addresses that are used in heap sprays. I wanted to compile this larger list. As you'll see, if you look at it, there's some repeating addresses. Sometimes the last character may differ sometimes, but not always. These are ones that are specifically enumerated by EMET 5.1 in their heap spray protection mitigation, which, when it's enabled for a process, when the CTORs and initialization code runs before it jumps to the main function, is going to pre-allocate dummy blocks at all of these addresses so that it cannot be used reliably in a heap spray. These are good addresses because they are easy to address, and they often align with heap regions in the general case, withstanding ASLR, of course. It's always a brute force in that dimension, and you can reliably use these without worrying about null bytes. So now to Clang. Clang is a C and C++ front-end compiler for the LLVM compiler platform. LLVM is commonly understood to be the compiler backend, doing all the intermediate language and compilation to the underlying assembly translation. And Clang, I also forgot to say, also handles Objective-C and Objective-C++. Its features compared to GCC are faster compiles with lower memory use. but many times, depending on the features that you compile with or the flags you compile with, it may cause slower code performance in some cases. It has better diagnostics and it has more security quote unquote features, the best of it being address sanitizer, or otherwise just called ASAN. It has been recently widely adopted by various Unix distributions, and notably, this includes Ubuntu, Xubuntu, and the whole Ubuntu family, Red Hat, BSD, and possibly several others. To compare how the Clang stack works, it's relatively the same. This slide has an example of some real simple C code. It's just a function named foo that calls printf and passes it the string test. Or rather, it's going to pass a pointer to it. We'll go through it line by line. On the left is the Clang compiled example. On the right is the GCC compiled example. The flags are listed for each, and no flags were configured outside of this. So again, this is just stock compile, no flags. Both do push EPP. Both move ESP into EPP to move up the stack frame. Then they subtract ESP by a pointer, 2 pointers. Then they move the pointer to the string. Here is just a push of a hard address. Here's the load effective address for this in the data segment into EAX, and then to basically push EAX. Instead, they do move EAX and onto wherever the top of the stack is. Then they both call print. So print will return the result of printf in EAX, and so it's pushing it on the stack here through EVP, which is interesting. But then they both move ESP back up by adding it. This does pop EVP. GCC uses leave more often, which is the same as pop EVP. It occasionally does other things. And then they both return. There's no big difference at this level. So where it really differs is when you start using flags for security benefits. Like GCC, Clang offers ASLR and stack fortification and stack canaries and Relro, but it also offers other new things like safe stack, control flow integrity, and format string attack mitigation. The efficacy of these is not really well understood for the community at this moment, and we're going to dive into some of the bad advice that people give. Specifically, where I've seen bad advice on Stack Overflow threads as well as hardening guides is the analysis of fstack protector, which gives you stack canaries, and comparing it to SafeStack from Clang. Now, SafeStack in Clang creates a second stack for tracking control flow data and other information. It uses different registers to a degree, and it makes it so that if one stack is corrupted integrity-wise, then it can jump to the other one and still handle whatever's going on. So it's designed to keep going in the case of a buffer overflow overriding critical information. Now, stack canaries are different. The epilogue of any function, there's going to be a call to check stack canary in either GCC or Clang compiled code with this mitigation, and it's going to check a 4 or 8 byte cookie that's going to be put on the stack right before the return address, maybe right before EVP, depending on the compiler. And before it gets to using that data, it checks whether or not the cookie's been overwritten. If it's been overwritten, it will stick abort due to the stack smash. And I've seen both in hardening guides as well as Stack Overflow threads, it's recommended due to the performance overheads of both of these, since they provide redundant security, to only use one or the other, but not to use both, because the performance overhead of using two stacks and two stack cookies on each, and then the checking code slows down code execution significantly. And this is happening per function. So to go over things quickly just for everyone, ASLR is enabled by two flags depending on the type of binary. For just standard binaries, you'd use PIE for position independent executable. For anything that's going to be linked in by a linker, such as shared libraries, you have to use PIC, position independent code. I don't know why they couldn't just make it under the same flag and make them interchangeable, but that's how it is, and that's how the linkers expect Clang and GCC compiled binaries and libraries. For source fortification, you'd use d underscore fortified underscore source equals 2. There's also 1 and 0, but 2 is the strongest, and that adds in some reordering of local variables and some additional checks. We've already covered stack canaries and safe stack. Control flow integrity is enabled by fsanitize equals CFI. It is actually experimental at the moment, so I can't outright recommend it. I have seen performance review experiments and papers that say it's actually quite good in terms of performance overhead, so it's not going to kill most processes. Railrow can either be partial or full, and it's enabled by this series of flags. It's not as straightforward to understand. It's just one of the things you got to memorize. And finally, format string attack mitigations are enabled by wformat, wformat-security, and warn on error format security, or werror. Clang offers actually a number of benefits for people looking to build introspection into their target applications for fuzzing. And fuzzing can either be for secure development lifecycle or bug hunting or etc. This is going to cover some flags that are actually just terrible in performance but give great introspection. Typical slowdown introduced by any address sanitizer or ASAN flags is at least 2 times. So address sanitizer is fantastic for detecting pointer bugs and use after free bugs, and it is enabled by fsanitize address. Something to note when compiling for introspection is if you're looking to fuzz a target and its libraries, say VLC, to gain introspection into the libraries, you have to recompile every single thing it imports and every single dependency that it has if you want to go that deep with these attributes. You can also detect undefined behavior, which again goes all the way back to lecture 2 when we were talked about integer bugs and how they're actually quite common in crypto libraries, which is just unacceptable. And so undefined behavior sanitizer is enabled by fsanitize equals undefined. And the use of pointer after scope is similar to ASAN's use after free detection, and that is enabled by fsanitize-address-use-after-scope. And so that would be distinct from use after freeze for the case that you have a local variable you're using, you're returning the value of a function through it, and then once it returns, that stack space is no longer protected. Hint, hint, that may be on one of the exams. Finally, format string exploit warnings are enabled by this. We've already covered it. And out of bounds checking can be enabled by warray bounds and werror equals array bounds. So I decided to look into Clang's safe stack mitigation. I just used the following code. Int main, it takes in argv. I just have a 4 byte buffer and I store copy into it from standard in. Or sorry, the first command line argument. And then I returned, and I only compiled it with Clang's fsanitize equals safe stack. And so I passed it one character, it's fine. I pass it more than 4 characters, and it doesn't segfault. It doesn't crash. That's interesting. I passed it a ton, and I passed it even more, and seems good. So I then break out the bash escape to run some Perl, and I give it 2 kilobytes of A's, and it segfaults. Exploit mitigation should never segfault. At worst, it should sigabort. This is how proper mitigations work. So there's something extremely wrong here. I decided to break out GDB. I basically ran it with run space $ parentheses Perl this whole statement, and it breaks then at the segfault, and this is the line of code it's segfaulting on. It's moving into ESI some pointer at EBP plus EDI. And so looking at the registers, right now we control these following registers in terms of 41s, and it seems that only EVP is under our control at the moment. EDI, right now it looks like negative 76. So instead of setting in a ton of A's, we can then completely override EVP. Now it gets more interesting. And this next slide, I have highlighted all of the lines of code that lead to actually exploiting this flaw in their mitigation. So since we fully control EVP, EDI may be some variation at any given time for the general case. However, being an index in this case is probably going to be in the low integer range, and it can be tested for and adjusted for. Now, what is happening is that it is taking EVP, is adding this offset of EDI, and it's loading that into ESI. It's testing to see if ESI is 0. If it's 0, it's going to jump here, but that's easy enough to avoid. Besides, you're overflowing it, and you can't overflow it with all zeros in most stir copies, so that's not going to be a problem. And so some irrelevant code happens, and it then uses ESI again. So what it's doing here is moving the pointer held by ESI into EAX. It's rotating it by 9 bits to the right, and then it is finally XORing it with this value. And then at the end of it, it calls EAX. I guarantee you that this is a bypassable mitigation. I don't know why Clang released this. It's pretty easy to see that they didn't test it sufficiently at all. Many mitigation developers just test it for general small cases and don't do anything significant. So here's my theory on why this breaks down. The two stacks are probably a kilobyte away from each other in terms of separation in memory. Even with the ASLR on, they probably are separated by a fixed amount of space. And we're overflowing from one into and through the other, which is allowing us, when pop EVP happens, to corrupt the integrity of EVP entirely, and then we're getting handled by this call detours where it's trying to deconstruct everything, which is very interesting. So I don't know if that's true. It's simply just my theory. At the end of my analysis, it is not clear why Clang's safe stack is purported to be a alternative to fstack protect. In other words, stack canaries. I understand the performance impact of using both. However, just this meager amount of testing has revealed serious flaws, if not complete vulnerabilities within the implementation. So, when you have hardening guides and community advice saying just go ahead and use SafeStack, it's the newer, better mitigation, um, and people who don't know better and who don't test it just adopt it, it's kind of it's disheartening. Um, Anyways, moving on. So, when you don't trust your developers, and I'm not talking about the developers of your compiler, but the developers of your organization and your system, systems, there are ways to force compiler mitigations by default so that they are present even when someone just does gcc foo.c, right? And the code on the left is just a stock compile. The code on the right is the same flags, just gcc foo.c, from a very hardened system that forces these mitigations by default, including stack check, so stack canary check, and fortify source, and other things. So there are multiple ways to do it. You can check your default flags in GCC with dump specs. I'm not sure if there is a similar one by Clang. For your make files, you can do /configure and then export C flags to be whatever you want. So fstack protector, fpi, relro, etc. And then you can make. For CMake, there is a tutorial here on how to make global defaults for your flags. And so you can do that for any compilers that CMake will use. And finally, you can use it with Alias, but this is better off for single users because it gets saved in the bash RC, and same for echoing here. If it's only going to get stored in a single user's bash profile. And so this is useful again for when you don't trust your developers in your organization to use all the security mitigations, and not the vast majority of universities do not produce developers with literacy in this arena. So it's something that often I advise to take into your own hands. You have to understand at the end of the day that it can affect performance. So again, we covered ASAN and all of those. If you're forcing all of those mitigation flags, you're going to have a huge performance hit. So this brings us to finally the developers of your Linux distros and of your operating systems. Binary distributions like Debian, Red Hat, CentOS, etc. all distribute pre-compiled binaries, and you have to trust their compiles if you're going to use them. I've done some research, and I've done a lot of interviews of people in the community, and just looked into asking people to run checksec on their system for all sorts of operating systems of binary distros. And my finding is that are they using performance optimization flags in their compiles? They're not always. But what's worse is, are they using exploit mitigation enforcement or compatibility flags? And the answer is actually most of the time they do not use all the available options, even when it costs them nothing in performance. And I'd point you all to the previous lecture where we looked at checksec for Ubuntu 15.04 and just saw all the apt-get packages that didn't have Pi support, didn't have Railroad, and it was just crazy. They're just so exploitable if it's part of your attack surface. And so the real alternative here is to compile your own distribution from the source code. It is not impossible. We teach people to do it. It just takes a few hours with the right hardware, you can see hardened Gentoo, BSD, certain configurations of Arch Linux, LFS, and Minix is also very worth mentioning here. There are definitely distributions that do this, and the difference is quite clear. On the left, this is latest Ubuntu 16 something, and we see with VirtualBox and everything else installed, there's no Pi support. There's no canaries on the stack for some of them. Partial railrow is everywhere, so you can just do GOT overrides all day long when you're doing exploitation. But on the right, you can see that everything is enforced. Everything is on. And if you really care about security of your systems, this is the way to go, because you can just laugh off the disasters that everyone else has to face almost on a daily basis. It's 2016. Organizations are getting owned all the time. So now let's talk about exploit mitigation suites, because this is um, what adds on to that additional security of enforcing everything. You can then force even stricter policies and exploit mitigations with these suites. Windows has EMET, which stands for Enhanced Mitigation Experience Toolkit. And can be found at this following link. Linux has GRSec, PAX, and kern heap patch sets that can be compiled into the kernel. If you have the kernel headers and sources, you can recompile your kernel at any time with these, and then reboot or kexec that given kernel to implement these new mitigations. I'm not sure if anything exists like this for Apple, and it definitely doesn't exist for mobile platforms, um, at least not in this nature. So let's dive into EMET. Some people call it Emmet. That always throws me off. The latest version of this lecture is 5.2, and it entails the following mitigations. Structured exception handling override protection, SEHOP, is something I used to cover in the original class, and overriding SEH stacks. SEHOP is a very effective mitigation that has kind of mitigated entirely this class of stack overflows. Um, the next one is dynamic data execution prevention. And this is a mitigation that enforces DEP, so it makes it illegal for data sections to be marked executable. Null page allocation prevention is a mitigation that prevents allocation of 0000 space for mmap or anything else for exploiting null pointer dereferences. This is more useful on Windows Embedded, as microprocessors often or allow this more often. Next is heap spray allocation prevention, which we just discussed in, I think, slide 3, and how it pre-allocates the dummy blocks at those given addresses. Mandatory ASLR forces, regardless of whether or not the compilation flag was used at the time of compiling the binary, it forces the base address randomization for all imported modules, even for legacy modules which do not have ASLR compiler support at all at their compilation time. Export address table filtering, EAF, is is a mitigation in which it tries to prevent how normal Windows shellcode often iterates over the export functions table to resolve and link functions used for the payload. Similar to how we described the dynamic shellcode linker in the previous lecture. ROP mitigations is an entire group of mitigations in EMET, and they encompass memory protection checks, caller checks, stack pivot prevention, and simulate execution flow. This is a suite of mitigations from ROPGuard. It's an independent project that was brought into EMET because it was vouched for and tested and found to be favorable. Stack pivot and simulated execution flow are somewhat more effective than the rest of the mitigations. Loaded library checks is a mitigation that prevents the loading of DLL files by universal naming convention paths. So using strings in your shellcode to force the loading of a DLL to have more capabilities is explicitly what that mitigates. Deep hooks. This is something that I've seen as an actually exploitable feature of EMET that allows attackers to bypass EMET. And you can find it on the next slide. More discussion of this. Anyways, this feature allows EMET to hook both critical Windows APIs and lowest level API functions to check their abuse and whatnot. Anti-detours is mitigating detours, which is somewhat of it's in the family of hooking. I believe we covered it back in the rootkits lecture. Banned functions is just a blacklist of abused functions that attackers often use during shellcode or payload execution. Certificate pinning or trust pinning is a great policy that requires code executing on the system to have a valid certificate signed by a known good third party that Microsoft trusts. It's really great against file system based malware and the standard download and run, click and execute social engineering phishing malware. Attack surface reduction is something that is less effective, mainly because the normal user can't set it up effectively. It is a blacklist and allows you to blacklist modules to forbid their import on a per process basis. So no user is going to know what modules are safe to blacklist per process because the modules for, say, Firefox and Chrome aren't going to be the same for Dropbox, aren't going to be the same for VirtualBox. They're not going to be the same for Open Office and Microsoft Office and everything else. So this is something that, since I've looked into it, there doesn't seem to be standards suggested settings per process released by Microsoft. It's something that it's has the potential to be good, but no one's going to go up and set it up individually like that. And finally, EAF Plus is additional protection of export table filtering of kernel 32, NTDLL, and kernel-based.dll. And this is all from the blog down at below by FireEye. So, for 80% of all Windows processes, you can bypass EMET incredibly simply. It is hilarious and sad at the same time. The WoW64 subsystem provides support for executing 32-bit processes on a 64-bit edition of Microsoft Windows. And according to Duo.com's The Duo Security Team's empirical research, they found that approximately 80% of all applications are WoW64 applications. At a high level, the WoW64 subsystem provides kind of a layer for handling the following: file system redirection for System32 to the appropriate system's syswow64 subsystem, registry redirection for 64-bit versions of the registry, exception handling differences for the differences in 64-bit native exceptions, and system call redirection, because you should all know that 32-bit and 64-bit system calls always differ in implementation, and so that has to be wrapped too. A neat feature about the WoW64 subsystem is that it allows to switch between 32-bit and 64-bit execution environments. For attackers, this means actually you now have at least, well, I don't know about at least, but almost that, double the gadgets. Because you can now treat everything as a 32-bit instruction as well as a 64-bit instruction, as long as you find the gadget to jump between the modes. And so the link provided here by the Duo security team dropped, I think, back in 2013, a incredible finding that 80% of all web browsers are actually 32-bit applications running on a 64-bit system through the WoW64 subsystem, and that if you use an exploitation of these targets, a 64-bit ROP chain and a simple secondary stage that really just targets one gadget, it makes it trivial to bypass all of EMET's mitigations. And so I encourage all of you to read more about it at the provided link. For the other 20% of applications that are either pure 32-bit or pure 64-bit, there are still mitigation bypasses that are of serious concern. There's one here at the FireEye blog and the SecConsult blog. And if you want to see a demo of it in action, there's a link here below. Now for the Linux side. GRSec is a long-running patch set that's been around for longer than the EMET patch set from Microsoft. It's at grsecurity.net. It involves PAX, which is going to be discussed in the next slide, and a number of other mitigations. Reuse address attack protection, which is a series of ROP mitigations, as ASLR, that's stronger than the stock one that comes with most kernels. Kernel space privilege escalation mitigations, which is a series of protection of common privilege escalation attacks and reducing the attack surface and mitigating techniques that attack them. Better stack protection, hardened userland memory protections, a thread stack protection. Threads have individual stacks, and sometimes they share variables or share references to variables, and so this is useful in some cases, some rare edge cases, where that can open up vulnerabilities. And then there are other mitigations that cover things outside of kind of exploit development. So they cover file system hardening for integrity protection, which can be more concerned for privilege escalation. They have miscellaneous other protections, role-based access control, which is really nice, and GCC security and compiler plugins to force those default mitigations in some cases. PAX joined the GRC security team at some point, and it is a Linux patch, kernel patch to provide executable safe space protection. And it is pretty much installed alongside of GRSec now these days. Its main features are NX, seg mem exec or segmexec, page exec, and these are software-based NX implementations for processors that lack the NX bit support. They have additional mitigations for mprotect and mmap, which is very interesting because it's designed to mitigate some of the techniques that we've discussed thus far for ROP. And finally, the ASLR additions randomize the stack segment base and specifically randomize the mmap code within the text segment or whatever object segment is in. You can see more at the link below. So GRSec and PAX have both been adopted together by default in Hardened Gentoo, Tor, Ramdisk, Alpine Linux, Copperhead OS, which is specifically just for 3 mobile devices. It's an Android spinoff. It's one of the only hardened Android systems I know of, and Astra Linux. These are all worth mentioning. I mentioned Hardened Gentoo a lot because it's very well known, and they have a lot of innovations tested out on the cutting edge in that developer space. KernHeap is specifically a patch set to mitigate kernel exploitation to achieve rootkit privilege escalation, and it drastically changes the kernel heap allocator and is considered a heap allocator hardening. It is a very strong mitigation against kernel heap exploitation, which is possibly one of the most common ways to get into the kernel. There's a FRAC article from its initial release, linked above, and after that is the link to the patch set that you can download and compile it for your kernel and then reboot and use it. Now, since I've gone this in depth into the mitigation patch suites, I felt like covering SE Linux SE Linux stands for Security Enhanced Linux. It actually came out of the NSA Security Enhanced Linux team. They decided to get together and publicly release what they're doing, I guess, I don't know, for the NSA side. Um, you can read about it on Wikipedia. It says it came out of the NSA, so it's got to be pretty good. And it is specifically a kernel module for enforcing strict access controls for files and resources. It does not focus on exploitation mitigation, so it's not in that family, but is worth talking about since we're covering system hardening. One thing to note before I get into all of this is that historically, SE Linux does not play well with GRSec and PAX. There's a few things that they overlap on, especially file system hardening and integrity controls that they don't play nice on. So SE Linux alone offers the following features: a clean separation of policy from enforcement, well-defined policy interfaces. It is not too bad to write policies for SE Linux. API support for applications, querying the policy and enforcing access control, so you can have application support for mandatory and discretionary access control and role-based access control, depending on the context. You can have separate measures for protecting system integrity and data confidentiality. You can have controls over process initialization as well as inheritance for program execution. You can have controls over file system directory files and open file descriptors. And I think pipes also. It should be in that list. And named pipes. And you can have controls over sockets, messages, and network interfaces. You can set resource limits based on roles, users, and etc. So that's very good for preventing any one user or service from being DDoS and taking down the whole system. You can have controls over the use of capabilities for capability-based systems, and you can have cached information access decisions via some access vector cache. So there's a number of other features as well. But the link to it is up above. Well, at least for Wikipedia, it should be relatively easy to find because it's very well known. So the final notes to wrap up this lecture is that the Clang version used for this lecture was 3.8.0 from Ubuntu 16.04, which is the LTS version. And in conclusion, you shouldn't always believe the security hype of people who say, hey, the latest and greatest thing is out, you gotta adopt it now. And that is simply because in security, time is one of the best judges of success. And there's been one thing that's always held true, and it's attributed or named Schneier's Law after Bruce Schneier. And it's that anyone can build a system that they cannot break into. And so this seems to be the case with Clang's safe stack that we just demonstrated is actually a new vulnerability. And other conclusions are that you should use exploit mitigation suites for your systems. You should always force both ASLR and DEP. And keep in mind that sometimes the libraries that you rely on are compiled without PI or NX support. So if you distribute binaries, you should consider redistributing securely compiled binaries of your dependencies. 3. You should always check your systems with checksec. That script is just, it's great. You should run checksec --kernel and checksec --procall and see what you can do to tighten up some of those gaps. Finally, if you are hardcore about security, you should really consider building your own hardened Linux systems. I have demonstrated the just systemic vulnerabilities and weaknesses in most modern binary distributions. And we at Hack All the Things offer a nice one-day, less than about 8-hour class on how to build, manage, and harden from source a hardened Gen 2 system with all of the latest mitigations and going through all of the GRSec and PAX configuration and system lockdown. At the end of the day, you can't always rely on other people to do the job right for you. You can't rely on them to develop the code securely. You can't rely on others to provide you third-party libraries that have been compiled to be compatible with even
I don't know, these some of these things are 10 years old now. Basic mitigations, and that finally goes for your operating system. If you have the source code, you can't always expect that it is being provided to you if it's a binary distribution in a with security or even performance, as we've seen being a major concern for the devs. Anyways, that is it for today's lecture. I hope you all learned a lot and enjoy.